Mechanical energy extra practice. This is pretty much designated for my pre-AP students. If you're not pre-AP, you're welcome to watch, but you will not be held responsible for this knowledge, nor the worksheet. All right, so here's all of our formulas. Okay, so there's your kinetic and potential energy formulas. Kinetic energy rearranged solved for mass and velocity. Potential energy rearranged solved for height and mass. Here's our mechanical, kinetic plus potential, and here's a rearrangement where we have the initial kinetic and the initial potential energy added together, and the final kinetic and the final potential energy added together, and they're set equal to each other. So this goes off the idea that the mechanical energy is constant throughout the system. Any 2 points, so a point initial and a point final, those are going to add up and equal each other. Okay. 75.5 kilogram rock is sitting on a 68.3 meter ledge. Then it falls from the ledge. I'm going to walk you through this. I don't expect you to understand it. I'm going to walk you through it to understand it, and then we're going to work from there. So, problem-solving process, 75.5 kilograms. Kilograms measures mass. 68.3 meters. This case, that meter ledge, we're talking about the height. 68.3 meters going up. So that's our height. Okay? First it asks, what is the kinetic energy of the rock? So right here. Kinetic energy, what is it? Well, it's just sitting there. The kinetic energy is 0. Next question, potential energy. What is the potential energy of the rock at the top? Well, potential energy, definitely not 0. Our potential energy, it's got lots of height, it's got lots of mass, so it definitely has some potential there. Potential energy is mass times gravity times height. Mass, 75.5. Gravity, we're going to use 9.81 for significant figures. And height, 68.3. In your calculator, you will get 50,586.7365. Significant figures, 333. So we have 50,600 joules. Okay, the 505, the 8 rounds that 5 up. But those 2 zeros, even though they're not significant, they are necessary placeholders. So, potential energy at the top, 50,600 joules. It's a lot of joules. That's a lot of energy. But it's just potential, just sitting there waiting. Okay, so what is the mechanical energy of the rock at the top? So mechanical energy is the kinetic energy plus the potential energy at any one point position. So the kinetic is 0. The potential is 50,600. So my mechanical energy at that position, 50,600 joules. Okay, now it's going to ask, what is the mechanical energy of the rock just before hitting the bottom? So that rock falls right here, okay? Hasn't actually hit the bottom yet, but where it's pretty much run out of height. The first question asks, well, what's the mechanical energy? Well, the mechanical energy we said was 50,600 joules at the top. Mechanical energy. Refer back to understanding mechanical energy. Mechanical energy, what do we know about mechanical energy for a system? It's constant. So it doesn't matter if it was here, or if it's here, or if it's here, or there, anywhere, any position along there, the mechanical energy is always going to be 50,600 joules. Now, it asks, what is the kinetic energy of the rock just before the bottom? Kinetic energy at the bottom. So, right here, kinetic energy. Just before we hit the bottom? Well, that's a good question. I'm going to skip first question number 6. The potential energy here at the bottom. Potential energy at the bottom. Remember, potential energy, mass times gravity times height. Height is now 0. So my potential energy at the bottom is 0 because there's no height. So if my potential energy at the bottom is 0, my mechanical energy at the bottom is 50,600. What's my kinetic energy at the bottom? Well, the kinetic energy is the mechanical energy minus the potential energy. 50,600 minus 0, 50,600 joules. All of that potential energy, it was just sitting there waiting, has transformed as it falls. It goes faster and faster and faster and faster, but it's lower and lower and lower. The potential energy all transformed into, went from 50,600 to 0. But the kinetic went from 0 to 50,600. Lots of kinetic energy. All of that potential energy transformed into kinetic energy. Okay, so the very last question. What is the velocity of the rock just before it hits the bottom? Well, if you look up here, formulas for velocity, ding, there's only one. Velocity is equal to the square root of 2 times the kinetic energy divided by the mass. So the velocity of the rock just before it hits the bottom, well, we know the kinetic energy at the bottom. We know the mass. We just plug it in. Square root of 2 times that 50,600 divided by the mass of 75.5. And when you're going to put that in the calculator, you get the little square root symbol, then comes the parentheses, and 2 times 50600, and then divide 75.5, and then close your parentheses. When you do that, your calculator will say 36.6114. Significant figures? Well, back up here, we've got 3 there, we've got 3 there. When we're using gravity, we did 3. So 3 significant figures, 3, 6, 6, 1, not going to round the 6 up. So 36.6 velocity measured in meters per second. That's one fast-moving rock when it gets to the bottom. All right, so there's the concept. Now, apply it. Get you started, and then I want you to work through this problem. So, 4.5 kilogram ball. Okay, so that's actually really, really massive. Okay, that's like a bowling ball. So picture this is Thor. Okay, and he throws a bowling ball straight up into the air with a velocity of 15.8 meters per second. That's velocity. That's all the information we get from that question. Okay? That's it. So, working through this thought process, step by step. What is the potential energy of the ball initially? So, you look at this and you go, well, I don't know because I don't know the height. We're making this point where he lets go of the ball our reference point. And because we can choose a reference point wherever we want it, if that's our reference point, then we can say, yep, that's going to be 0 potential energy because we're going to say at that point it has no height. So, a no height at that initial position at the bottom. So my potential energy is 0. Kinetic energy. What's my kinetic energy at the bottom? Well, that's at the moment he's let go, so at that point it's going very, 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 very fast. Velocity and mass, we can solve for the kinetic energy. Okay? So, if you have not attempted this yet, pause and attempt this. Okay. So, kinetic energy. 1/2 mass, velocity squared. 0.5 times the mass, 4.5, times the velocity, 15.8 squared. Don't forget the squared. It's the most common mistake. Even I make it quite frequently. Calculator says 561.69. Significant figures. Back to our original numbers. 2 sig figs, 3 sig figs, so our answer should have 2. So, the 5 and the 6, 2 sig figs, is the one going to round the 6 up? No. So 560 joules of kinetic energy. So, right here, we agree that the potential energy is equal to 0, because we're making that a reference point. And we just calculated the kinetic energy to be 560 joules. Next question, what is the mechanical energy of the ball initially? Pause if you haven't answered that question yet. Mechanical energy is the kinetic energy plus the potential energy. The kinetic at the bottom is 560, the potential at the bottom is 0. 560 plus 0, 560 plus 0, 560 joules. Okay? Mechanical energy at the bottom. Sorry, mechanical energy at the top. Mechanical energy at the top. So, we saw that the mechanical energy here at the bottom was 560 joules. And it's asking now for the mechanical energy at the top. Well, mechanical energy is constant in this system. It doesn't matter where you are in this system, whether the ball's right there, whether it's right there, whether it's somewhere in between. It doesn't matter where it is. The mechanical energy is going to be 560 joules because that's constant in this system. So it's 560 joules at the top. So, now we're going to the top. The question asks, what is the kinetic energy at the top? Okay, so kinetic energy at the top. The ball goes up, 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 up. When we talked and learned about projectiles, projectile motion, when an object is thrown straight up into the air and comes back down, when it reaches the apex, that highest point, what happens to its motion? It stops. It's not moving. So, the kinetic energy is 0 because ball is at rest. It stops for a split, like a very fraction of a second. It stops at that highest point. So its kinetic energy is 0. All right? So what's the potential energy at the top? So, next question. Potential energy at the top. What's it going to be? Well, the mechanical energy at the top is 560. The kinetic energy at the top is 0. Potential energy. Your potential energy is your mechanical energy minus your kinetic energy. The mechanical is 560. Anywhere along there. At the top, the kinetic is 0. So, 560 joules is my potential energy at the top. These two added together have to equal that. If that's 0, therefore, if my kinetic 0, my potential must be 560 for them to add up to equal 560 mechanical. So, what is the height of the ball at the top of the apex? Height. Well, look at your formulas. Only one solves for height. Okay. Potential energy at the bottom, no, at the top, sorry. Potential energy at the top. We already established that. 560. Mass, 4.5. Gravity, 9.81. Now, notice those parentheses. Super important that you put those parentheses in the calculator, or you will get the wrong answer. 560 divided by parentheses 4.5 times 9.81 close parentheses. Okay? Let me show you what I'm talking about. 560 times divided parentheses 4.5 times 9.81 close parentheses. Calculator says 12.6854. Okay? Now, significant figures on that. 2 sig figs that are smallest one, 2 sig figs, the 1 and the 2, 6 is going to round it up, so we get 13. It was asking for height. Wait. Up here again. What is that? It's asking for this right here. The height. How high did that get? From the bottom, what we called our reference point, all the way to the very top of the apex. How high is that? (13 meters). Now, for the sake of emphasis on using this calculator correctly, watch what happens to our answer when I remove those parentheses. Notice that this is nowhere near that. Order of operations. The calculator is saying, okay, I'm going to take 560, I'm going to divide it by 4.5, and then I'm going to multiply by the 9.81. That's not what you need. You need to multiply the 4.5 times 9.81, and then you need to take 560 and divide it. So be sure you include those parentheses, or you're going to get the wrong answer. Okay. On to the back side. These are definitely pause, attempt the problem, and then I'll show you how to work it out. If you get part way through the problem and you get stuck, go through the video till you get unstuck, pause it, and then move on. Okay? 15.0 kilograms. Measures mass. 3.50 meters per second. Measures velocity. And the question is asking for potential energy at the top. Now, it should kind of jump out and be like, wait. Potential energy. Potential energy, if you think about your formulas, potential energy requires mass, gravity, and height. I don't have height, I have velocity. Velocity is for kinetic energy. Yes, that's why you have to pay attention to what the question's saying. Okay? The ball is thrown into the air. Here's the ball. Thrown into the air, and it goes up and 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 up. That right there is the top. Okay, the apex. So, This mass and velocity, that velocity applies to what's going on down here. The mass doesn't change, doesn't matter where it is. So I have the information, the mass and the velocity, to calculate what? Kinetic energy. 1/2 mass velocity squared, but the kinetic energy at the bottom. 0.5 times 15 times 3.5 squared. $91.875 joules. Okay, that is my kinetic energy at the bottom. 91.8. So significant figures. 1, 2, 3. 3 significant figures. That 7 is going to round the 8 up, so it's going to be 91.9. 91.9 joules of kinetic energy at the bottom. Now, remember how this works. This isn't asking these questions, but they're necessary for you to process. I've got 91.9 joules of kinetic energy at the bottom. How much potential energy do I have at the bottom? Well, if we're at the bottom, my potential energy is 0. So I have all of this kinetic energy. That makes the ball go up, 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 and gets that highest point. At that highest point, my kinetic energy is now gone. I no longer have kinetic energy. It no longer is moving. For a split second, it actually stops. So, at that very, very tip-top point, what happened to all that kinetic energy I started with? Well, it got the ball higher and higher and higher and higher and higher, so it all turned into potential energy. At the top, I have 91.9 joules of potential energy. And that's the question. How much potential energy will I have at the top? 91.9 joules. Okay. Question number 2. Pause and give it a try. We have a 5.5 kilogram ball, mass 6.5 meter high ledge, height. Okay, if it's pushed off the ledge, how much kinetic energy will it have just before hitting the ground? So, give myself a little picture. Sitting at the top. Pushed off the ledge. Just before it hits the ground, it's going really, 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 really fast. And the question asks, how much kinetic energy will it have at the bottom? Well, I know the height, 6.5 meters. I know the mass, 5.5 kilograms. I can solve for the potential energy at the top. Mass times gravity times height, 5.5 times 9.81 times 6.5. Calculator says 350.7075 sig figs to 350 joules. At the top, I have 350 joules of potential energy. It's at rest, so my kinetic energy is 0. All that potential energy transformed, in this system, there are 350 joules of energy. in this system, there are 350 joules of energy. You can say 350 joules of mechanical energy, the kinetic energy is 0, the potential energy is 350, add them together, you get 350, however you really want to see that, okay? 350 joules falls, all of that 350 joules of potential transforms. As it goes lower and lower and lower, it loses potential, but it's going faster and faster and faster, so it's gaining kinetic. At the bottom, we will have 350 joules of kinetic energy. And that's the question. Next one, pause and attempt. .25 kilogram ball, mass thrown into the air, 11 meters per second, that's velocity, okay? So, again, ball goes up, 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 up. I have mass and I have velocity. Question is asking for height. If you take a look at your formulas, it doesn't, there's the height with potential energy, mass and gravity, and there's the velocity with kinetic and mass, and I don't know. You're gonna have to understand what's going on. So with these problems, sometimes the easiest thing to do is go, okay, what can I solve for? Draw yourself a little picture and ask yourself, what can I solve for? That meters per second, that velocity, is talking about the velocity right there. That's how fast it's going right there. So I can solve for the kinetic energy at the bottom. Right there, I can solve for that kinetic energy because I have the mass and the velocity at that point. 0.5 times 25 times 11 squared. Calculator says 1512.5 sig figs, just 2, so 1,500 joules. That's the kinetic energy at the bottom. At the bottom, because we're calling this our reference point, our potential energy is 0. So that potential energy transforms into, or that kinetic energy at the bottom goes higher and higher and higher, but slower and higher, but slower, but higher, but slower, but higher, but slower, but higher, but slower. Kinetic energy at the top is 0. Potential energy, all that kinetic transformed. We have 1,500 joules of potential at the top. Now to the question, height. That formula is the potential energy over the mass times the gravity. We know the mass. Now we know what the potential is at the top. We can plug it in. So, potential 1,500 divided by parentheses, your mass 25 times gravity of 9.8. 9.81. Okay, so when you put this in the calculator, don't forget the parentheses. All right, and the calculator is going to look like this. Divide, parentheses, 25 times 9.81, close parentheses. Calculator says 6.1162 significant figures, just 2, 6.1 height, meters. All right, next problem, pause first. 3.85 kilograms, measures mass. 0.875 meters. Ledge, that's going to be your height. If it's pushed off, how fast will it be going at the bottom? 8.75 meters ledge. That's less than that's less than 1 meter. That's like pushing it off a tall desk. Okay? A rock, that's a good sized rock. That's a bowling ball sized rock. Okay? How fast is it going when it hits the ground? That's a good question. Okay? So, we have here a question of velocity. Mass, height. But mass and height, so our scenario, easier to sketch it out. It's going to fall just before it hits the ground. It's going to be moving really, really fast. The question is, what's that velocity going to be? But I have the height and I have the mass. So potential energy is what I can solve for. Mass, gravity, height. 3.85 for the mass times 9.81 for gravity times the height, 0.875. $33.0474 sig figs 3 33.0 potential energy measured in joules. So at the top I have 33.0 joules of potential energy. Because it's at rest, kinetic energy is 0, so that total energy for this system, the total energy is 33.0. The mechanical energy is 33.0. So as it falls, that 33.0 joules of potential energy is going to get lower and lower and lower because it's losing height, less height, but faster, less height, but faster, less height, but faster and faster and faster and faster and faster. At the bottom, kinetic energy is going to be 33.0. Velocity is the square root of 2 times the kinetic energy divided by the mass. So, put in the calculator, square root 2 times 33 divided by 3.85. Calculator says 4.14039. Sig figs, 3 sig figs, 3 sig figs, 3 sig figs, 414, 0 doesn't affect it, so 4.14 velocity meters per second. Cool. Problem 5. 6.75 kilograms. Measures mass. Cannonball shot straight up into the air. So there's our cannon. Ball goes straight up into the air. Okay. 85.5 meters per second. That's its velocity when it leaves the cannon. Question asks for the maximum height. Height is our question. How high will that cannonball get? Well, let's find out, shall we? Mass and velocity are what I have. I can solve for kinetic energy using mass and velocity. That will be the kinetic energy at the bottom. Okay, I can solve for the kinetic energy at the bottom. 0.5 times 6.75 times 85.5 squared. Don't forget the squared. Don't forget the squared. Calculator says 24672.09375. Sig figs, 3 sig figs. 2, 4, 6. 7's going to round the 6 up, so 24700. 24,700 joules of kinetic energy at the bottom. Potential energy at the bottom is 0, because we're stating that as our reference point, where it leaves the cannon. Goes up, 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 goes fast, goes slower, but higher, but slower, but higher, but slower, but higher, but slower, but higher, stops. Kinetic energy equals 0. Potential energy. All of this kinetic energy transformed into potential energy. 24,700 joules. So my height is my potential energy at the top divided by mass times gravity. Don't forget your parentheses. 24,700 divided by parentheses 6.75 for the mass multiplied by 9.81 for gravity. Close your parentheses. Calculator says 373.013 sig figs, 3 sig figs, 3 sig figs, 0 is not going to affect, so 373 meters high. It's pretty high. Last one. 1.55 kilogram coconut. That is a coconut for King Kong. That's massive coconut. 15.8 meters. All right. Mass. Hanging 15.8 meters above the ground. That is the tallest coconut tree ever. But that's fine by me. So we have our tree. Coconuts are palms, I believe. Here's your coconut. .8 meters high. Mass of 1.55 kilograms. And it falls right before that coconut hits the ground. How fast is it going? Velocity is the question. Well, I have mass and height. I can solve for potential energy. Mass, gravity, height. 1.55 grams, gravity of 9.81, height of 15.8. Calculator says 240.2469. Sig figs 333. 1, 2, 3. 2 is not going to round it up. So 240 joules of potential energy at the top. So we have 240 joules of potential energy. Well, if it's just hanging there, velocity is 0. So the total energy for my system is the 240 joules. That 240 joules, as it falls, it gets lower and lower and lower, so less and less potential, but it's going faster and 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 faster. So it's gaining kinetic. The kinetic energy at the bottom will be 240 joules. Formula for velocity is the square root of 2 times the kinetic energy divided by the mass. Kinetic energy at the bottom is 240. So square root 2 times the 240 divided by the mass of 1.55, close parentheses. Don't forget, square root 2 times 240 divided by 1.55. Calculator says 17.5976. Significant figures, 333, 333, 9's going the 5 up, so 17.6. Velocity in meters per second. There you go. End of the worksheet.